Welcome to Fun with Science, Engineering, and Technology. I'm Mr. Ross, and today what we're going to do is we're going to investigate some currents, some air currents, convection currents, and we're going to some deep sea water currents. Right? So I have Melissa and Catherine with me today as my assistants, and what we'll do first of all is we're going to start out, I believe, and we're going to take a look at some deep sea ocean currents. Right? We have a deep ocean over here, our container filled with some water, which is right at the moment at room temperature. And we're going to take and set it up. First of all, we're going to put in one corner of it some ice in a beaker with a little water and set it down in that corner right there. Now, oceans, right, the reason we did that is that they're not always the same temperature. Down towards the equator, for instance, the sun beats down on them a little bit longer, and they're going to be what?
Warmer.
A little bit warmer. If we go up to the North Pole or the South Pole, where the sun doesn't beat down on the ocean as much, and they're going to be what?
Colder.
Colder. So we got cold spots in the ocean, we got warm spots in the ocean. And that beaker of ice I just put in there is
Cold.
a cold spot. Right. Now, what we're going to do next is we're going to make a hot spot. I have some boiling water over here, which is, what's the temperature of boiling water? Anybody, you remember?
100 degrees.
100 degrees Celsius or 212 degrees Fahrenheit. Now, watch out very carefully. Back up just a little bit. Now, these beakers we have that I just put the water in are made out of Pyrex, a special glass, right? And they shouldn't break when we got hot water in here. We're going to put it down in that relatively cold water, and it shouldn't break, right? But if somebody happened to have dropped this beaker at one time and maybe cracked it a little bit, it might. So, but normally it won't break. So we're going to set it down in there like that, right? So we have the North Pole over here, right, with the cold beaker, and over here we have
The equator.
some part close to the equator, someplace a little bit warmer. Right? So what we're going to do now is, what should happen? Do you have any idea what might happen?
Nope.
All right. Well, you did properties of matter. What happens to the matter when you heat it up a little bit?
It goes down.
It gets less dense, right?
Yeah.
Right? So if it's less dense, it's going to rise. Like the density towers that you made, the less dense ones were where?
At the top.
At the top, and the more dense ones were down at the bottom, right? So, yes, if we think back about that a little bit, we have the hot water over there, and what it's going to do is it's going to heat up the water around it in the tank, and as it heats that water up, what's going to happen to it? It's going to get less dense, and it should rise up to the top. The cold one over here is going to make the water around it colder, right, and make it more dense, and it should sink down to the bottom. Right, so what's going to happen is, if we think about it a little bit, is maybe we should get a current that runs around, right? Starts here and goes around, gets to the hot, comes up, back across the top, back down, back across the top. Okay? Can you see anything happening?
No.
No. All right, so what we're going to have to do is we're going to have to put some dye in there. And I have some crystals here. And we're going to put over here by the cold side. Isn't that pretty?
Yep.
That's pretty. It's nice and purple. Some purple dye. Now, what's happening to it?
It's going toward the hot.
It's going over towards the hot side.
But it's staying on the bottom.
But it's staying down on the bottom. So we put those crystals in, the crystals fell down to the bottom. So it's going over towards the hot side, right? Going from the cold to the hot. And then when it gets over there, what do you think is going to happen to it?
It's going to go up.
It's going to go up, right? And then where's it going to go?
Back to the cold.
Back to the cold. Okay, that's going to take up a little bit for that to happen. So while that's going on, let's take a look at some air currents now. Right? I have a couple towers here, basically. Some containers, right, with big tubes on the top of them, right? And there's no water in here, but there is air. So what I'm going to do is I'm going to take, I have a candle, a little candle. What's this thing?
A lighter.
A lighter. How's it light? You remember that? Well, from way back when we did electricity.
A spark.
There's a spark, all right. What generates the spark? When we pull the trigger, we bang on a little crystal in there, and it was called, I know you don't remember that, it's piezoelectric effect, okay, which generates a spark. It's going to, and if we make it work right, it's going to light this candle up here, right? So what I'm going to do is I'm going to put the candle under that tower there. Now what should be happening? Candle is doing what?
It broke off.
Right, but what's the candle doing? It's heating up the air, right? It's hot.
Yeah. Yep.
Right? So the candle's heating up the air, right? Making the air in there warmer. So what should happen to the air as it gets warmer?
Go up.
So it should go up, right? It becomes less dense, becomes more buoyant, and it should go up. Now then, if I go on this side, and I put a beaker full of ice underneath there, now what's that ice going to do to the air?
Make it go down.
It's going to make it cool it off and make it more dense, right? So that it should go down. So what should be happening here? Tell me, what do you think should be happening? I've got candle over here heating it up, and I've got
the air from the eye is gonna go to the candle.
the air from the ice
And
is going to go
be
through.
heat up, and it's gonna go up.
It's going to go up,
And then air from here is gonna
and
sink
the air
to the
from here is
bottom.
go down. Okay, yeah, that's a good hypothesis. How can we tell?
You can't really,
We can't see because we can't. Why not?
because air is clear.
The air is clear, right? What we need to do is we need to do something where we can see the air, and we're going to use another guy's old thing, which is called the Tyndall Effect. And what Tyndall Effect is, like you're sitting at home and there's a lot of little dust particles in the air, right?
Mm-hmm.
Can you see them?
Yeah.
Right, but why can you see them? Because the reason you can see them is because the light is reflecting off those dust particles. You can't see anything that light doesn't reflect off of. The air molecules are so thin, so small, that we can't see them because the light doesn't bounce off of them normally. But if there's dust in the air, or fog, or clouds, or smoke, then the light is going to bounce off of those particles because they're bigger, and we're going to be able to see them. So what we have here is a punk stick. You know what punk is?
No.
It's sort of decayed wood, right? It's wood that's sort of started to decay, decompose. So what we're going to do is we're going to light it. It doesn't really burn with a big flame necessarily, but it'll smolder. And guess what? We have smoke. Okay? So what I'm going to do is I'm going to take this, and we can see that smoke, right?
Yep.
That's because of that guy named Tyndall, okay? We named that effect after it. And the reason we can see it is because all the light is reflecting off of those smoke particles. So I'm going to put this down in here. I'm going to fill my column up with some smoke. And if everything is working just right, all right? Can we see what's happening to the smoke?
Yeah.
Where's it going?
It's going down.
It's gone down? All right, and let's put a little more in there so that maybe we can see it. All right, it's still going down?
Yep.
Yep.
All right. Is there any started to go across here just yet?
Not yet.
Not yet? Okay. Make sure we have a good tight connection here because we don't want to lose any air pressure. What's happening to our, while we're waiting for this to work, what's happening to over here? What
It's
happened?
at the top.
It's, a, it's
What?
at the top by the coal.
It's going
All right,
like a
it went up, across, and up, right? And then to come back across the top. If we get down and look at the side of it, can you see down on the side? Right. What about in the middle, right down in here, right in here? What do we have? Is there anything there?
No.
It's going toward the hot.
It's going towards the hot, right? So that die, when we look at it, it's going across, up, it's going from the cold, right? Because cold water, this cold beaker is causing the water to become more dense, and it's going down, right? Going down this way, and then it flows across the bottom. It gets over to the hot beaker where the water is a little bit warmer, and it should be going up like this, right? Up to the top, and then it flows back across over here like this. And we have an ocean current then. Basically what we've done is we built a model of the ocean current, right? It's like the Gulf Stream out in the Atlantic Ocean. It starts down in the Gulf of Mexico and comes up past us and so forth. All right, I think we have a little problem. We don't have a good connection here, and we're probably losing some of the airflow. So, but what would happen if it wasn't for a missed connection is the smoke would come down, right? Go across here, be heat to the hot air, up, and come back up out this tube over here. Okay? Let's take this off a minute and see what happens when I put it in here. Okay, so that's a convection current, right? Put a smoke in here, it comes down to cold air, denser air is going to sink down to the bottom, right? The candle is heating up the air, which should come up to the top, and we should have a convection current. We should be able to see the smoke go all the way down, right, through this tube, up here, and back out the top of that one. Okay, so, now what's our ocean current still over here?
It's going back toward the hot.
It's going back towards the hot. It's still working?
Yeah.
Right. Now that's very important. Both of these currents are very, very important because they're going to affect our weather. And what you're studying right now is you're studying what is the unit you're studying? Do you remember? It's called natural catastrophes, right? And it's like hurricanes and tornadoes and volcanoes and all those sorts of things. And these have a very important effect on our weather. Okay. So what we do was get rid of this for a moment. Put out the candle. It's not my birthday, so you don't have to give me any presents. Right? So that's very important, right? Because what it does is it conducts the energy from one part of the ocean to the other with that current. Also, it's important for the sea creatures that are out there because what is happening is that current water flows, right? It's picking up nutrients off the bottom of the ocean, bringing them back up to the top where most of the creatures are, and they can get food that way. So it's very important not only for our weather, but also for the sea creatures. There are a couple lakes down in Africa, right? They're in volcanic craters, and they don't have any currents like this. And one morning, back in about 1986, they found 1,800 people and all their animals dead that lived around that lake. Ooh, right? That's a natural disaster, right? They didn't know what was happening, so what they did is they called in all the scientists from all around the world. And they decided, okay, these lakes are in volcanic craters, and they're real deep. They're about 700 feet deep. And since they're at the equator, there's no change in temperature, basically. So there's no current set up in the lake, right? Because it doesn't get hot and doesn't get cold. It stays basically the same temperature. So there are none of those convection currents in the lake. And since they are in volcanic craters, the volcanoes are still a little bit active, and one of the things that you'll probably find out when you get to studying volcanoes, right, is that they release carbon dioxide, right? And since there's no currents, no convection currents in this lake, right, the carbon dioxide never comes up to the top. And it's like a big soda bottle, right? What makes the soda fizz? Carbon dioxide, right? That's why it makes your Coca-Cola and your Pepsi-Cola and all those things fizz, is because they put carbon dioxide gas in it. Well, this lake is like a big soda bottle. Carbon dioxide coming off the volcano, the extinct volcano, gets trapped down at the bottom, right? And stays there and builds up and builds up and builds up, right? And then if something happens, like maybe there's a landslide where the rocks come down in, hit in the lake, and stir the water up a little bit, it's like taking the cap off your soda bottle, or shaking your soda bottle, right, and taking the cap off. What happens? All that carbon dioxide comes out. So what had happened to these lakes is that they had a rock slide come down in, stirred the lake up a little bit, and all that carbon dioxide come up. Right, now carbon dioxide is not, by itself is not poisonous, but if you get enough of it up and fill this room with carbon dioxide, guess what? There's no oxygen. So if you don't have any oxygen, what are you going to do? And that's what happened to these almost 2,000 people and all their animals, right? Is that one evening, around 8 or 9 o'clock in the evening, there was a rock slide that came down, stirred the lake up a little bit. It was like taking a soda bottle, shaking it and taking the cap off, and all the carbon dioxide came up and filled the surrounding area with carbon dioxide, pushed all the oxygen away, and all those people suffocated. You know how they fixed the problem?
How?
The big straw. Just like the straw you put in your soda bottle. Right? What they did is they went into the lake, right? And very carefully, because they figured if they stirred this lake up a little too much, it was the same thing was going to happen. And what they did is they put a pipe all the way down to the bottom of the lake. When they put the pipe down and stopped the pipe, guess what? Water started shooting up because it released all that carbon dioxide, and the carbon dioxide had pushed the water up. And so they can let the carbon dioxide out of the lake with those big pipes that they put down in the lake. And hopefully they don't lose 1,800 people again. So, what's happening over there? We still have a current going?
Yeah.
Yeah.
Okay. Let me have... We're going to do, this is all very basic principles that we have, right, that we were talking about. And basically it revolves around the density of different materials, right? And the less dense materials have a tendency to do what? Float up to the top, right? And the more dense they are,
Goes down.
they're going to go down. It's a very basic principle. So what I have here now is I have 2 beakers of just plain old water, sort of at room temperature, right? And I have over here a dropper with some cold dye in it, right? It's been sitting in the ice for quite a while. Some of that purple dye again, right? That's room temperature, and this is very, very cold. This is down around 32 degrees. Now what I'm going to do is I'm going to drop some in there, right? What do you think should happen to it? Which is the most dense now?
The cold.
The cold one. So what's going to happen to it? It's going to go to the bottom. Okay, let's watch it and let's look at it very, very carefully. I'm going to put a little drop in there. What happened to it?
It went right to the bottom.
Right to the bottom, right? And what is going to happen is after it gets down to the bottom, what is going to happen to all those little molecules of dye? They're going to start spreading out. They're going to diffuse, right? And spread out, and eventually our thing will be the same. Look at it. Does it all go down and just one big drop fall down to the bottom, or what happened to it?
It's separated.
It's separated a little bit, right? What if I were to, okay, so it's like a little pattern to it, right? So let me do this. Let's try that again. I'll try it again. All right, now you watch it. Again, let's see what happens. Does it have the same, what happened? It still went down to the bottom, right?
Yep.
Right, because it was more dense. Same pattern?
Yep.
Same pattern as before?
No.
Yes.
Come on, let me, I'm not going to empty that one
No.
out again. I'm going to put another one in. You watch
It didn't do the same thing as last time.
It didn't not exactly the same thing, pattern, right?
It didn't do the exact same.
It's not the exact same pattern. It went down, but it's not the exact same pattern. My question is, right, all this weather stuff that we have is all based on some very basic science, right? Science that you've learned in 6th, 7th, and 8th grade, right? You know that more dense air comes down, right? Warmer, less dense air rises. We have ocean currents and so forth. Why is it so hard to predict the weather? It's all, you know, just basic science. There's nothing really complicated about the science behind what causes a tornado, what causes it to rain. That's condensation, the water cycle that you've talked about. What do you think makes it so complicated to predict the weather? How come these guys can't predict our weather the next day? You know, they say, well, we think the sun's going to come out, and what does it do? It rains, right? How's come?
Because it's different.
It's different, right. The same basic science, all right, put a drop of cold dye in there, it sank to the bottom, but the pattern was different every time, right? So if we could predict what the pattern was going to be, that's what they're doing when they're predicting the weather, is they're predicting the pattern of all these little basic science things that are going to happen, right? Which is a very, very difficult thing. There's all kinds of variables, as, you know, how high up I held it when I dropped it, the exact temperatures that I had, right? Whether the drop was the same shape, right? Whether the same amount of material in the drop. All those things were variables, right? And we have so many variables, we can't really predict what that pattern is going to be when it starts to diffuse. All right? So now then, I have one here that's hot, right? And another beaker of good old room temperature water. What do you think is going to happen if I put a drop of this in there?
It's going to stay on the top.
It's going to stay on the top? Oh, come on. You kid, how do you know that?
Because it's less dense.
Because it's less dense?
So it's going to stay at the top.
What did it do? It's going to eventually sink a little bit because of the weight of the molecules, but does it sink as fast?
No.
And it basically stayed up on top, right? Because it was hot, it was less dense, right? But it's going to eventually diffuse a little bit down through the bottom. Right. So, what we've done, our first experiment was here. We simulated a deep ocean, right? And we put a beaker on one side with ice in it, beaker on the other side with boiling water, and then we dropped some dye crystals in it, right? And what happened then is this cold water, right, and hot water is, over here is eventually going to heat up the ocean, right, and cause it to rise. The cold water is going to cause the water surrounding the beaker to sink, right, and it's going to sink down and go across the bottom and up, and back across the top, right, and give us a little current. And for that dye, is exactly what we saw happen. It's probably diffused enough we can't really see the difference now, right? We can't see where it's going. It's probably not an open space in here. Right? So that was one experiment that we did. Right? The next one was find the right page. This one, right, where we had two columns, right? One with a candle on one side and
One with ice.
one with ice, all right? So the one with ice, what was going to happen to the air in here?
Would go down.
It should go down, right? The ice is going to cool the air down. The air is going to become what? More dense, and it's more dense, it's going to sink. The candle is going to heat up the air
air's
and make it
less dense.
less dense, so
it's
it should
gonna
go up. So when we took our little punk stick here and lit it up and put smoke in here, right, and used that guy's Tyndall's effect, right, because that smoke scatters the light, we can see it, right, and the smoke should have gone down, going through the tube here, and back up this side here, right. Now the air current, if the air current was really, very strong, it would have gone down, up, back over here, and back down again, but just like the ocean current. But the currents aren't strong enough to do that in this particular case. Ours didn't work very well. You know why?
Why?
Why? Because what happened is we didn't have a good connection right here. Our little tubing in here wasn't big enough, right? So what is happening is the cold air, this smoke was sinking a little bit, but didn't make a complete circuit. You needed this one over here to make it warm and pull it up. So when this warm air was pulling up, instead of dragging the smoke through the tube, what was happening was it was dragging in more fresh air, and we didn't get the smoke over there, so we didn't see it. Right? So that's what happened to our little experiment. Our tube wasn't very good connection. Then, what do we do next? We did another one, which, if I can find it very quickly here. That's right. We had 2 beakers, right? Room temperature water. We had 1 little bottle of dye, which is in the ice cube, it was very cold, right? And we had another bottle of dye, which was in the hot water, right? And we started off first, we put a drop of the very cold in the room temperature water, right? And what happened?
It went straight down.
It went straight down and spread out a little bit, right? We tried it a couple times. Was the pattern how it spread out the same?
No.
No? And that's why those guys that do
Can't
the
predict
weather
the weather.
forecast can't predict the weather for tomorrow. The hot one we put, and it did eventually drop down, but initially it sort of
slowly.
stayed right on top, and it was a lot slower when it descended, right? So that's one of the basic causes of all our weather, and it's based on some very simple scientific principles that we've all studied in 6th, 7th, and 8th grade. And the reason we can't predict the weather is because
The patterns are different.
because the patterns are different. We can't predict that pattern. There's a theory that says, right, and I don't know how true this is, but if there's a monarch butterfly that flaps its wings down in Mexico, it's going to have an effect on our weather, right? So I don't know whether that's true or whether that's sort of a myth, but that's one of the things. All right, these are very simple experiments which you can try at home. You don't need the fancy dyes that we had. You can use food coloring, and I'm sure that you have a tray that you can try that deep ocean experiment with and have a little bit of fun with it and amaze all your neighbors and friends. Thank you very much. We'll see you the next time.